But otherwise, I've been facing issues with the application problems. Somehow, I've not been able to like solve them, really frame up, formulate the equations and all. Till week 4, somehow this was not an issue, but this time it is. So yes,
Okay. So can you,
especially yes.
yeah, so can you specify which problem exactly it is, so we can maybe look at that?
Yeah. So the week 5 deadline is over. So I think we can pick up the grading assignment problems also, right?
Yeah.
Yeah. So let me just open the portal.
Yeah.
Uh, week 5. Graded assignment. Okay. So like for example, question 7. Let's say. Uh, uh, yes. So there is one set of questions 7, 8, 9, and then there is 10, 11, 12, 13. So maybe if we could take a look at one of them here, and then maybe I could try the other one later myself to check if I'm.
Yeah, sure. So
Uh,
7.
yeah.
Yeah. So we present that window.
Okay. So you will present.
This is the question, right? This.
Yes. I mean, how to like solve this in matrix terms, specifically the eigenvalues, eigenvectors. That part
Yeah,
somehow
sure.
has not been obvious to me.
Yeah. Let me just quickly read the question. Discrete time weather model where XNS is the probability that the weather is sunny on day n. Okay. Yeah, like, just give me 1 minute. I'll just okay. This, they have formatted it kind of very inconveniently. So working.
Yes. Yeah, a little bit.
Yeah. They should have. They should ideally wrap around anyway. So xn s xnr. Okay. So this is. So probability that the weather is sunny on day n. Okay. XNR is the probability that the weather is rainy on day n. Okay. On any given day, if the weather is sunny, then there is a 70% chance it stays sunny. Okay.
Yes.
And next day, 30% chance that it becomes rainy. Okay.
Yes.
So if you condition on the weather being sunny, then 0.7 is the probability
Probability. Yeah. Of.
it will stay sunny the next day, and 30% it becomes rainy the next day. Okay. If you condition on uh, rainy, then 0.4 that it becomes sunny, and 0.6 stays
Yes.
sunny.
So when I was doing, I was getting the opposite order. I mean, this main diagonal from the answer. The main diagonal remained the same,
Okay.
0.7, 0.6 as it should be, but the order of zero point 0.4 and 0.3 was reversed in my answer.
All right. So let me just draw this table. So this is a 2x2 table, right? So let me maybe have this table. So there is the weather is sunny. Okay, the weather is sunny, rainy. Okay, so that is the current weather, right? I believe this is like maybe current weather. So xn. Okay, maybe we call this xn. Okay, so this is n, and then this we can have this to be n, and this is for n plus 1, and this one
Ah,
is
okay. Yeah, this makes
plus
sense.
1, right? Okay, so if it is sunny, the weather is sunny, then there is a 0.7 probability that it will stay sunny the next day, right? So this is 0.7, right? Is this
Mm,
correct?
yes.
Okay, and if it is rainy, then there is a 60% chance it stays rainy. Okay, so this is 0.6 then.
Yes, yes.
Okay, then what does it say? If the weather is sunny, then there is a 70% chance. Okay, 30% chance that it is rainy. So the next day. So if it is sunny, then there is a 30% chance that it will be rainy the next day, right? And here
Yes,
it is 0.4. So zero point 0.7, zero point 0.4. That is how it is 0.7, 0.4, 0.3,
yes.
0.6.
Yeah,
Okay,
yeah.
so
Intuitively, yeah, this makes sense. Yeah.
right, so now, yeah, you just have to plug this into a matrix 0.4, 0.3, 0.6. And if you call this as your current, what do they call it? They call it XNR, right? So XNS XNR. Therefore, if you, okay, how do we get from here to that, right? So point, there is a certain probability. Okay, let us first write down these equations. So there is a certain probability that it is currently sunny. So you want the probability that it will remain sunny the next day, right? So that is what is on the LHS. So if we want to do that, there is a certain probability with which it is currently sunny. So then you multiply so that even this is one possibility. Alternatively, there's a possibility that it is currently rainy and then it becomes sunny, right? So it is currently rainy and then with zero point 0.4 chance it becomes sunny, right? So this is okay, right? This is the first equation.
Yes, I think I was tripping up because I thought the probability should always add up to 1, so point 0.7, point 0.7 should be
Ah,
like,
okay.
I
Right, you're
thought,
right. Probability should add up to one, but then
yes,
the yeah, this one will add up to one, right? So these two add up to one, but then not. So what we are looking at is, so this xn plus one s and xn plus one r, right? So those two. So let's go ahead, right? And those two should ideally add up to one. So this is zero point
yes,
0.3.
I mean these are not mutually exclusive. Okay, the
Right.
standard probability doesn't apply in that sense. Yeah, okay.
Yeah, yeah. So just to complete this, what will happen? So this is like if it is sunny and you want it to be rainy, then it's zero point 0.3. And if it is already rainy and you want it to remain rainy, it is xnr, right? So this is nothing but the, so xn, so this is xn plus 1, right? So this is xn plus 1 comma s and xn plus 1 comma r becomes now 0 0.7, 0 0.4, 0 0.3, 0.6. Yeah. So 8 times this.
Mhm.
Yeah, so that is regarding the setting up the equation, right? So the transition matrix. And then what do they ask? Assume that the initial weather distribution is x naught. Okay, it's 100% sunny on day zero. What are the weather distributions of?
X1 and X2. So I think this time we plug the values and find the answer basically.
Right, right, right.
Yeah,
Yeah. So zero point 0.7, zero point 0.3, and then
yeah. Maybe if you can just work out as well, so I can.
yeah. So this is x naught. So this is x naught. So we have so x naught we have. Let me take this matrix. So x1 is what we need, right? So x naught we have. What do they say? X naught is 1 0. Okay, 1 0. So if you multiply, you get x1 comma s, x1 comma r, right? What are the weather distribution vectors? X1 and x2. Okay, x2 is like you multiply it once more, right? So this is x1, right? This is x1. So I think what they mean by x1, even though they haven't explicitly given it, is x1 comma s, x1 comma r. Right? So this is what they mean. So this is nothing but x0 comma s and x0 comma r. And then if you uh, plug in, so let's maybe write this as a times x. So and then we can use this a here so that it becomes a times 1 0, right? So this will just remain 0.7, zero
Yeah,
point 0.3, right? So sorry, that is the
yeah, yeah. Point three.
point. Okay? So then and then I guess x2 is just one more time you multiply. So this is
This time we'll use X1 as the for input, right?
right, exactly. Yeah. So this is x2. So everything will change to now x2 x2, and this one will become x1. So rest of it will just be
the same.
same thing, but with just this one changing to 0.7, 0.3, and
Yes.
so I believe 0.49 and
0.12.
yeah, right, exactly. So
it would be 0.61 something. Yes.
this
Then
one is
0.21 plus 0.18.
right. Yeah, so this will end up being
0.61 and 0.39.
0.61 and point. Yeah. So these two, as you see, have to sum up to
39. Okay.
yeah.
And if we check the answer, yes.
61. So it's 39. Yeah, sorry,
Yes.
39. Right. So 6139.
Yes.
That
Okay.
is what this.
Yes. Okay. This one is also fairly. This one was fairly easy. Okay. Question number 9. Right.
Yeah.
What is the general formula for the better? Okay. Now I think this time they are asking us to generalize the what we just did.
Right.
But using this additional thing called diagonalization. Okay. I think this I don't have familiarity with. So maybe.
Yeah. Yeah.
Uh,
So right. So what we can do here is you first of all we need to get hold of this general formula, right? So what we see happening is if you want x1, then you need to multiply it by a once. If you want x2, you need to multiply it by a twice. So you could actually write this as a square into x naught, right?
yes. Yes. We can
So,
see that. And yeah.
generalizing this, if we want xn, which is the same as xn or xns and xnr, then we need to multiply pre-multiply, right? Basically,
Yes.
pre-multiply x naught by a power n. It's n times. So each one will give you one extra one increment. So which gives us xn equal to a power n x naught. Right. So x1 is a x naught, x2 is a square x naught. This is fine, right?
Yes.
The,
Yes. Yes.
so all that we need to do is make use of what is called diagonalization to get hold of a power n. So have you gone through this idea? Do you know what diagonalization is?
No, to be honest, I think
Okay.
yeah.
Okay, so diagonalization is this idea that there are there is this concept called diagonalizability. Okay, uh,
Yes.
diagonalizability.
Yes. Yes. That's fine.
It's correct, right? Yeah. So
This yeah. You have to remove this A, but yeah, fine. Yeah.
okay, okay. That is why. Okay, right. So diagonalizability is this idea that there are a matrix, square matrix, right? So a square matrix A of order n is said to be diagonalizable
Yes.
if there is an invertible matrix P and a diagonal matrix D, okay, such that you can express PA as P into D into P times P inverse, right? So A P D P inverse is this is the idea of diagonalizability. So there should be a way of decomposing this is a this is a way of decomposing
Hmm.
a matrix into a product of three matrices, okay, out of which you can see that they are slightly simpler matrices. So one is diagonal matrix is quite simple, right? So
Yes. Only the main diagonal elements are non-zero.
yeah, P is of course P need not be simple, but still, so this kind of what is the analogy? So the analogy, or rather the connection you can make is with prime factorization, right? We have done prime factorization in school, right? So in high school, you
Yes.
decompose numbers into the simplest as a product of simpler numbers.
Simpler numbers.
So in a similar sense, it's often a good idea to decompose a matrix into smaller, not smaller matrices, but other matrices.
Yeah. So it's a prime factorization of matrices.
In a sense, yeah.
Yes.
So that covers it. So what is the use of diagonalization? One use this process is called diagonalization. So matrices which can be diagonalized are called diagonalizable matrices. Okay, so diagonalizability is the area of linear algebra that talks about or discusses this idea of diagonalizable matrices. Okay, so what is the use? One use, right, is that we can easily deal with powers
Powers.
of matrices, right? That is the main idea. So, or rather, that's one of the uses. That's not the only use. So, for example, if you want to do a square, so it is just PDP inverse uh, multiplied by PDP inverse. Okay, so
Mm.
though this looks complex, what happens is if you expand it out, so it becomes PD. I'm just grouping it
Yeah,
conveniently. So
rearranging, I think. Yeah,
yeah, so the P inverse P is just I, right? So
yeah,
it's the identity.
this is identity. Yeah.
So it becomes P D square P inverse,
Mm.
and therefore this raising it to the exponent. So an exponent of diagonal matrix is very simple, right? So it's
Yeah,
just that.
it is easier than, yeah, the main.
So in general, what this helps, why this helps is if you want a power n, you can extend this and say that it's nothing but PD P power n P inverse, right? So all that you need to do is just multiply by P and P inverse on both sides, and D power n comes for free in a sense.
Yes. So how do we select this suitable matrix P?
Exactly. So that is the idea. So now, how do we diagonalize? So the idea is, of course, I'm not proving anything. That I think you can refer to the lectures. It
Okay.
turns out that if a matrix C, first of all, you have to understand that not all. So there are, before we go there, right? The first thing to understand is that though this seems very alluring to do, not all matrices are diagonalizable, unfortunately.
Mm.
So that's the first thing. Now,
Yes.
if a matrix is diagonalizable, how do we diagonalize? So that's the next question. So that the question therefore becomes what is the algorithm in some sense? What is the procedure is what we're asking. So the idea is you I'm stating all of these things without proof, right? So the matrix P is nothing but, or rather the columns of P, right? So the columns of P are the eigenvectors of it. Okay. And the columns, the diagonal elements of D are the corresponding eigenvalues. So if you can find the eigenvalues and the eigenvectors of A and add them to the columns of P and the diagonals of D, then you are done. So that is the procedure, or that's the algorithm as we call it.
Okay.
Okay, so that's we can let's just write out. So A power, what is A for us? A is, so do you do you know how to find eigenvalues, eigenvectors? Are you familiar with that?
Yes, some basic ideas.
Okay,
Um,
maybe we can discuss that
yeah.
also. I don't think
Okay.
anyone else is going to join, so we can just as well do that. So eigenvalues and eigenvectors, right? So maybe first we start with how to compute eigenvalues. So you have to solve what
The,
is called the solve for the characteristic polynomial. So we
yes,
have to set this.
the determinant should be zero. Yeah.
Yeah. So let's just do that. So zero point 0.7 minus lambda, 0 0.4, 0 0.3, 0 0.6.
Minus lambda.
Right. So this is 0. So an easy way to write this is actually lambda square minus the trace of the matrix. So of course you can expand the determinant, but as a shortcut, you can just add the
Trace the
diagonal, right?
diagonal, the sum of the diagonal elements.
Yeah, some of the diagonals and plus the determinant of the matrix. So this is like 42 minus 12, right? So 42 minus 12 is 30, right? So 0.3, I believe.
Yes.
Is that correct? Let's check. Supposed to be. So lambda square minus 1.3 lambda, right? Plus 0.3. Okay, let's just pause for a second. So this 0.7, zero point 0.6 is 13, so 1.3, and then 0.42 minus 0.12, right? 0.32, zero point 0.3. Okay, so this is fine, right? So this so far.
I mean, you use that shortcut, so I'll have to.
Yeah, yeah. So shortcut is so. See, the shortcut is following. It's very simple. It's actually a useful one. So there is this property. So eigenvalues have this property that the sum of the eigenvalues is equal to the trace of the matrix. Okay,
Yes, and the
and
product is determinant.
correct. So exactly. Right? So eigenvalues is equal to the determinant of the matrix. So therefore, what is happening is here the characteristic polynomial. So this means that the characteristic polynomial can be written as lambda square, any characteristic polynomial, of course, for 2 cross 2. So this will not work for 3 cross 3 or 4 cross 4 or higher orders. But so in general, you can write it as, see, in general, what is it? It's lambda 1 minus lambda into lambda 2 minus lambda, right? So if the two eigenvalues are lambda 1 and lambda 2, that is the characteristic polynomial. So what we can do is we can actually, if you expand, you will see you'll end up getting lambda square minus lambda 1 plus lambda 2 lambda plus lambda 1 lambda 2.
And then this lambda 1 plus lambda 2 is nothing but the trace, right?
Exactly. Right. So that is how, that's the trick. So it's not a trick really. So it's just trace of A times lambda plus determinant of A. So
Oh,
that's what we have done. So what we have done here is lambda square minus 1.3 lambda plus 0.3.
yeah, then it looks good. Yeah.
Okay. So then what we have is we just have to solve for. So this is what 0.3, 0.3 is 30, right? So 30, how do you get 30? 0.1
Maybe
plus,
maybe just directly use the quadratic formula. I don't.
correct, correct, yeah.
Because
So
the decimal point, yeah, a little bit hang up. How to factorize?
right. So alternatively, let's see if this will work. Will this work? Is this going to work? So this won't work, right? 1.3 will come, but then okay, this seems to work. So lambda square minus 1.3 lambda.
Uh, yes.
This, yeah, this is like into plus 0.3, right? So yeah,
Minus
so I
one.
guess this
Yeah,
works. So
yeah, this works. Yeah.
the eigenvalue, yeah, or alternatively, yeah, you're right. So the quadratic formula is safest. So it then, if you are able to, if you're not able to quickly find it, then yeah,
Yeah, of course, that is the last resort.
right, right, yeah. So this is the eigenvalues, right? So we have found the eigenvalues. So now eigenvectors, for the eigenvectors,
We
what?
we plug these eigenvalues back into the uh,
Exactly. So we have to now plug a minus lambda 1 into I into some eigenvector v is 0, right? So
yes,
this is the 0 vector.
yes.
So we just have to solve now. So this is a is what? 0 0.7, 0 0.4, 0 0.3, 0 0.6. So 0 0.7, 0 0.4, 0 0.3, 0 0.6, and we are doing minus lambda 1. So lambda 1, let's say is, so let's say we are doing this first for lambda 1,
Let's do for V first. Yeah.
right? So 1 minus, so this is 0 0.6 minus 1, and we have v1, v2, some vector, eigenvector v1, v2 is the 0 vector. So this is 0, 0, right? And so this becomes minus 0.3, 0.4, 0.3, and minus 0.4, correct?
Okay. Yeah, the first matrix. Yeah.
Okay, so that becomes that. And now we can just do elimination. So we can just, what we can do is add the second row, add the first row to the second row. So for example, so that you are familiar, right? So if you
Yeah,
add,
multiple ways to do this.
yeah, yeah, exactly. So we can actually, what we'll end up getting is, so if we set this zero, and we end up having this v1, v2, and
Yeah,
this
so a redundant. Okay, yeah. So we'll have a span of some vector basically
exactly, yeah,
as, as the yeah, as the eigenvector.
right. So what we could just pick up one of them. So maybe we can pick up
Yeah, parameterize.
yeah. So for this, we, for the p matrix, right, we just need one of the eigenvectors. So as you said, it's the entire span, but maybe we can, for convenience, we can choose v2 to be 1. So for example, if v2 is 1, then okay, so now v2 is 1 means I just want to ensure that we don't get too many fractions here. So maybe, so we, what is the equation? It's 0.3 v1 equal to 0.4 v2, correct?
Yes.
Okay, so what will help us is, let's say, if v2 is 3, so if v2 is 3, then
Uh,
uh, this will be like
For 9.9.
Yeah,
No,
point.
no, I mean, V1, we just need the ratio, right? V1 by V2 is
Yeah, yeah,
point 0.4 by point 0.3. So
yeah. It is just
we
4
can
by
make
3, right?
4 by 3, 4 by 3, yeah.
Okay, V1 by V2 is 4 by 3. Yeah.
And the span of this is the entire,
Right.
yeah.
Right. So this will. So this is one eigenvector, right? So
Yeah, of course. It's the
for lambda 1 equal to 1. So we just have to repeat the process now for like lambda.
lambda 2, right?
Yeah. So let's quickly do that also. So lambda 2 is 0.3, right? So lambda 2 is 0.3. Just going
Yes.
to copy not the entire thing, but yeah. So this is minus zero point 0.3 and this is minus zero point 0.3. Sorry, minus zero point 0.3. So this becomes zero point 0.4, right? Zero point 0.4 and zero point 0.3.
0.3, again positive.
This becomes zero point 0.3. So once again, we are left with, so we can make this 0. The second row can be made 0
Oh,
because, right, you can divide by 0.3, second row becomes 1, 1, and then you can just get rid of that. So here it is simpler. So we can just have 1 comma minus 1 as is an eigenvector, right? So it's just the
mm,
ratio is,
yes,
minus 1, right? So
yes.
the span of that. So what is P now? Therefore, we have all the ingredients for P and D. So therefore, we can form P and D. So we just have to be careful with the following. So the let's first add the eigenvalues in the diagonal matrix, right? So the diagonal matrix will have, it's usually a practice to have the larger eigenvalue first. So 1 in the first diagonal and first diagonal entry and zero point 0.3 in the as the second one. It's not a rule. So you can also swap them, but usually the larger one goes here.
Okay. Yeah, then we'll just follow that.
Yeah. So 4 comma 3 is this one. So 4 comma 3 is the first column and 1 comma minus 1 is the second column. Okay.
Oh,
So
oh.
that is then you just have to find P inverse. So do you know the trick to find P inverse
I
quickly?
mean, I remember the class 12 method, but is there any quicker way also?
Class
By,
12
by,
method.
by taking the transpose, so by taking the cofactors and then transpose and then
Okay. So for
using the adjunct method, I think. Yeah, that.
right. For 2 cross 2 alone, there is a slightly easier way to do it. So what you can do is you can swap the diagonal entries. So
Yes,
minus one.
and change the signs for the.
Exactly. Same thing. Same thing. So that is this.
Yeah,
This is
of course, 2 by 2 is easy.
right. Yeah. Not for, yeah. Of course, not for three cross three. Right. So 3 cross 3, I also don't know any shorter
Any,
way of doing it.
okay.
4. Yeah. So this is minus 4 minus 3. Right. So this is minus 7. So that
Mm,
is.
yeah, the determinant, right? Oh,
Yeah,
oh.
so that is all there is to. So now, if you actually do this, you have to verify this. We are yet to do that, but hopefully this is what we'll get. So A will be PDP inverse. If we multiply PD and P inverse, we should get back A.
Okay.
Okay, so that is diagonalization. This is
But
what we have done. So
we were calculating a square, right?
yeah,
Um,
A power n. In fact, right. That is what we need. We need
yeah,
A power n.
yeah,
So that
yeah.
so we will do that. So therefore, A power n becomes PD PD power n P inverse. And what is that? So A power n will be P is this one, D power n is this one. So this is 1 power n and zero point 0.3 power n. And P inverse is this whole thing. So minus 1 by 7. So maybe I'll just move the minus 1 by 7 alone in the beginning. So minus 1 by 7. Okay.
Yeah.
So what we see in the answer is they have multiplied the 3 together. So that's all. That's what we need to do now. So let's do that. So what do we get? It's a bit tiresome to do this, but we'll anyway do it. So 4 into
Uh, can you once review this? How did we do this d to the power n? Did we just take? I
d
mean,
power n is nothing but the
uh,
diagonal in entry power n.
okay, only the type. Yeah, because the rest are zero. So
Yeah.
okay.
So
Uh,
that
oh,
is, yeah, that's all there
okay.
is to that part.
Okay.
So okay, so this is just matrix multiplication, right? So I'm just multiplying these two first. So this becomes 4 and 0.3 power n, correct? 4 and 0.3 power n and 3.
We can multiply them in any order. I mean, like
Right, yeah, any order.
matrix multiplication is commutative. I mean, okay.
Associative, right? It is not
Yeah, no,
commutative. Yeah.
yeah, so, okay,
Yeah, so you could multiply these two first and then with this. You can
okay,
multiply these two first and then with this. Only thing you should not do is like change the order of the,
okay, okay,
like
okay,
swap the
okay.
order, right?
Yes, yeah, because okay, okay. Those two are different things. Yeah,
Right.
correct.
Okay, so this is 0.3 power n, and then I'm just adding the this fellow here. So that is one final multiplication, which should give us the answer. So this is minus 1 by 7, and this is minus 4 minus 0.3 power n plus 1, correct? So there's another 0.3. So uh,
Yes,
minus 4 minus 0.3 power n plus 1.
yeah, because we can add this 3 as 0.3 to the power. Uh, what I mean.
N into so zero point 0.3 power n plus 1, right? So just since you are just multiplying one more 0.3.
Oh, okay, okay. I've written in terms of 0.3. I was going in terms of 3. So okay, fine.
Right. So then minus 0.4, sorry, minus 4 plus 4 into 0.3 power n, right? So 4 into 0.3 power n. And then we have minus 3 minus 0.3 power n plus 1, and minus 3 minus 4 into 0.3 power n. You don't seem to be getting, so this minus, let's just take it inside. So everything becomes plus,
Yeah, yes, change the sign.
right? So plus, 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 except perhaps this one, right? Was this
The sign, yeah, it will interchange. Yeah, like this.
okay?
And
So
and
this one also is plus, right?
yeah, yeah, yeah.
What is answers? Let's see. What is the answer? 4 plus 3 into, okay, they have,
They have taken the n also, I think, as common. But
right. Oh, okay, they have now multiplied it by, so they want xn, right? So this is a power n. So we need xn. So xn is, so now finally what we need is xn. So finally we can,
one more round of multiplication.
yeah. So xn is a power n into x naught. So x naught thankfully is the first column, right? What was x naught? 1 0, right? X naught is the just, so if you multiply this with x naught is just the first column of the matrix. So you'll end up getting 1 by 7 into the vector 4 plus 0.3. Let's just write it like them. So zero point 0.3 power n and 3 plus 0.3 into 0.3 power n, right? So 4 plus 0.3 power n. Okay, they have a minus. Okay, so they have a minus. What is the, maybe while doing this we missed something. So
Yeah.
3. Okay, so 3 minus 3 plus zero point 0.3 power. Yeah, so this has to be minus, correct?
Yes.
Okay, right. So that this is okay, right? This is the, that is the
And
idea.
yeah, and then they took okay, okay. I mean, yeah,
Yeah,
it's
9
just.
is,
Um, by the way, I was reading on my own. I found this thing called Cayley-Hamilton theorem. Which is, I think, a simpler, faster way to compute powers of a matrix. Is it there in the course or in the lectures? Or?
it is. I don't think the Cayley-Hamilton theorem is there. Uh,
Okay, which yeah, it seemed a lot simpler.
okay, okay,
Yeah, but yeah. But yeah, I mean, if it's not in the course, then I think
right,
we
right.
have to flip it. So, okay. Um, okay.
Right,
Okay. 7, 8, 9. Okay, I think we have done all three of this set.
right.
Um,
Yeah. So any other questions that you have?
no, and if assuming the next four questions, 10 to 13, are also similar, I would like to do them on my own, of course.
Sure, sure. Yeah, I believe they. Yeah, I think they are similar. So
At
you
least
will
they
just
should, at least they should, yeah, follow logically or build upon. Then also I can live
correct,
with
correct.
that.
Yeah, I think so. So I say same. Yeah, it's the same sequence of questions.
Yes, and maybe you could share okay. You'll be sharing the recorded presentation anyway, right?
Yeah, I'll
Otherwise,
share this
this
sheet also. You can share this
yes, yes,
PDF.
Yes, it's excellent actually, because I think, yeah.
Yeah, sure. I can share this. So, okay. So what week 6 live session, right? Yeah, I can share
Yeah.
this.
So maybe in the supplementary content section or something.
Yeah. Let me take a look at that. I just want to ensure. Where is it?
I'm not sure if it has been created yet, or yeah, it yeah. I think on Thursday, yeah, we'll be
Okay.
getting
Yeah,
that.
sure. I can add it here. So
Yes, that will be great.
yes, sure. Let me think this will make sense only to you, I believe, not, or maybe those who join, those who watch the session later on, they may be able to relate. Yeah. Yeah.
Yeah, yeah, there
I'll
should
share
be.
this. Yeah. Okay. Anything else from any other question you want to discuss?
Uh, I mean, I do like to do things, try things on my own first, and
Yeah,
which
yeah,
is
that is the best. Yeah, yeah,
I think what is encouraged here as well.
exactly.
But other than that, if we could maybe take a brief look at Week 6. By the way, I would, since no one has joined yet, I also would like to leave max by 9 for dinner.
Yeah, yeah, sure, sure. Yeah.
But even then, I think we have a good 20 minutes left. Um, so what we could do maybe is, uh, yeah, Week 6. I mean, since it is still not the deadline is not yet come, so we can't touch the graded assignment. But maybe if a practice assignment can be pick up, or maybe even the activity questions, some those application oriented problems basically again.
Right. So week 6.
Or maybe if you have any additional questions of your own that you'd like to bring, that
Yeah.
will also.
Yeah. So not, I don't have right
Yeah,
now. I don't have any.
basically applications. Yeah, applications of whatever is taught in Week 6.
Okay. So week 6 actually is kind of more of matrix algebra. So it is.
Yes,
See what?
matrix and determinants. This is far more based on class 12, to be honest.
Correct. Correct. Yeah.
It does build upon that, of course, because otherwise it would be just to repeat.
Yeah. Yeah.
But
So
uh,
there are.
I
See.
think the notations are a little complicated somehow, but we get the idea intuitively. but,
Right. Right. Yeah.
yes,
Apart from that, right? So let's maybe quickly see what all there. So there are questions about inverses.
there are some properties, yeah, determinants, and first of all, there is classification of matrices, and then there were some properties of determinants and things like that.
Right. Right.
Yeah, and until there, I think no, I was fine.
Okay.
But yes, but then some of these uh, in the later questions, I think there will be some complicated notations or
Right. Yeah. If you
uh,
want, we can go over this practice assignment. We can go over it.
yeah. I mean, if it's fair game, yeah, maybe we can pick up some of the questions.
Yeah. So this is boring. Let's skip this.
Yeah,
So
yeah,
max.
yeah.
Right.
1, 2, 3, 4. I think these the first few questions will be probably easier also.
Yeah. Yeah. This might be interesting. So choose the set of correct options. So a triangular 3 cross 3
Yeah, I
matrix.
think again properties based question. Mm,
So you want more of the application.
yeah, more of because I think these also yeah, I can do on my own. At least I think
Okay.
these yeah, it would be good to look at the proofs and stuff also for these. So, but
Right. So you can tell me. So this, do you want to do this? See, this also is just
yeah,
application.
maybe let me just scroll them on my own.
Yeah.
This
Sure. Yeah.
because then.
You can maybe quickly go through it and let me know which one we can look at now. You want me to change, or you have it open at your end?
Sorry.
Yeah, you have it open at your end, right? So or
Yes,
you want?
yeah, yeah. I'm surfing through it.
Yeah, sure.
Uh, Somehow, I mean, these all are not that confusing at a first look. I mean, uh, uh, it was somehow only the graded assignment. So
Right.
I think we'll have to wait that one out. But yes, um, um, there is one question 9. I think. which I think might apply some of the ideas we covered today, because it is dealing in powers of matrices.
Okay, okay.
So maybe if you could take a look.
Sure. You want me to start working on this right away? Like, shall we start doing it, or do you like you want to try it? It's if
Uh,
it's if
I
it's fine,
think
we can directly start working on it.
maybe you only
Yeah,
show
yeah,
them,
it's fine
because
with
I'm
me.
sure there will be other questions left for me to try out, right?
Okay,
Later.
okay. So A is 1 0 minus 1, 1 0 minus 1, and 0 0 0, minus 1, 0 1. Okay, so if A power 100 is written in terms of A as A power 100.
Normally we wouldn't even keep the middle row, right? Or is it?
Right, true.
But,
So
um, so I'm just wondering if um,
yeah, so in terms of a system of equations, you are right. It doesn't make sense to have the second row. Second
yes,
equation is
at
just,
all.
yeah. But as a matrix, it still makes sense. See, because it is still a 3 cross 3 matrix, right? So
Yeah, I mean there are three columns, but yeah, but
right,
that,
right.
yeah, that is what we mean, that a row is redundant, complete
Correct.
entirely.
Yeah, yeah.
So, but okay, um,
So A power 100 is written as,
in terms
so
of
apparently A power 100 can be written as 2 power n 8. So we have to find out what 2 power what n is, right? So hint they have given us to express A power k in terms of A. So this is, see, the trick here is to just do A square, for example, and see if we have any patterns emerging. So we can maybe start with A square. So we can't do anything else at present. Only thing we can do is just
yeah, I
try
mean,
out.
the hint says use mathematical induction. So,
Right.
but that, as far as I remember, used I think one, and then some arbitrary integer m, and then m plus one, something like that.
Agreed, agreed. Yeah. So
So is this strictly related to that, or is there a more general
yeah,
notion of mathematical
it
induction?
is related to that. But the only thing is that we to to perform induction, we would need some kind of a formula in place, right? So something that says A power k is A power n is likely to be this, and then we can rigorously establish that using induction.
Mm,
So actually, there should have been, okay. There is another hint which you should have given if you want to like completely help the learner here, and that hint would be first compute A square. So I also don't know. So let's try and see. So if we compute A square, we might get a pattern, and then we can generalize that pattern. So that is where induction will come in. So let's see this. If we multiply, we might get a sense of what is happening. So this 1 0 minus 1, 1 0 minus 1 gives us 2, right? So 1 0 minus 1, this is 0, and that is 1 0 minus 1 will give us minus 2, correct?
okay, I was off the screen on there. Okay, so yes, one, yeah, zero. Then yeah, looks good.
Right. So this all of these are zeros. Then we have
But,
minus 1.
but wait, you are multiplying the two, right?
Yeah,
So
just a square.
oh, yeah, okay. Okay, that was good then. I was still stuck on the first row, first column. Okay,
Okay.
okay.
So this is again 0. So this is again 0, and this is 2. Right. So
Mhm.
that is a square. Now the question is there a pattern? So there seems to be a pattern, right? So wherever you have, I believe we can now, so we can now generalize and say that, let's say A power n is perhaps A power k they want. Okay, so let's call it A power k is perhaps something like k0 minus k 0 0 0, and then minus k 0 k, right? Assuming that this pattern will hold. So that is the idea.
Hmm.
Okay,
Yes.
now we can use induction. So we can now use
Oh
induction,
yeah. Okay. Yeah. Great. Now it makes sense.
right? So now maybe A power
We have to we have to first arrive at something to test using
exactly.
it.
Yeah. So that should have been the first hint if you want to really.
Yeah. Yeah. I mean that was not there in the question, so
Right, right.
but they should have provided maybe.
Yeah. So this is A power k into this matrix A power k into A again. So into A, and that is nothing but this is A power k according to our inductive hypothesis into A, right? So now we can just see if we are getting minus k. So we should get minus k. So k plus 1, 0 minus k plus 1. That's the hope. So let's see. So this is k into 0, sorry, k into 1. So we get, oh, okay. So I believe we get 2k. So that is, so what we assumed was wrong. So that is, I believe this is 2 power k.
Um,
Okay, let's see. So maybe we need to do one more step. So let me erase this. Let's do a cube, right? Let's see what we get.
okay.
Right? So let's do a cube and see where that takes us. We were a bit hasty in generalizing. So this is what? 2, 0, minus 2. So this is 4, right? And then
Um,
everything is
actually,
0. Then minus 2, 0, minus 2. So this is minus 4. So once again, 0, 0, 0. Minus 2, 0, minus 2. So this is minus 4. Once again, 0 and 2, 0, 2, 4, right? So this is a cube, right?
yeah.
So this seems to be therefore so a itself was 2 power 0. So a square was 2 power 1. So a cube is 2 square. So this is, you can maybe write this as 2 square 0 minus 2 square, and then 0, 0, 0, and minus 2 square 0, 2 square. So now perhaps we can generalize. We can hypothesize that this is a power k is equal to say 2 power k minus 1,
Minus 1,
right? So minus 2 power k minus 1, and then 0, 0, 0, and minus 2 power k minus 1, 0, 2 power k minus 1. And now we can try. So now we can try a power k plus 1 as a power k into a. So let's go back and see what is a is this. So if you now plug this here, hopefully we should get it. So 2 power.
yeah. Yeah, the order matters once again, or
Here the order doesn't matter. So when it comes to a power n, you can, it
uh,
is
yes, because technically, yeah, yeah.
right. So here order doesn't matter. So this is 2 power k minus 1 into 2, right? So this will be 2 power k and 0. Once again, this should be 2 power k and 0, 0, 0. I think this should work out. So 2 power k, 0, 2 power k, right? So in general, we can say that if you go back to the question, this is a power 100 should be, so they, okay, we can take this 2 power k outside. So in general, a power k is therefore, we have just established this using induction. So this is 2 power k minus 1 times, this is just 1 minus 1, 0 minus 1, and 1, right? So I think this is nothing but a, right? 1, 0 minus 1, 0, 0, 0 minus 1, 0, 1 is just a. So it's actually 2 power k minus 1 times a, and that is what they want. So this is a power k is,
yeah. Now we substitute n as
yeah,
k minus 1, I think.
yeah. So that is, I believe that should be,
That would,
yeah. So that is the,
yes.
right? That is the, that's the,
Yes, we got it right. Okay. And then just maybe one more question.
yeah,
Question 5, option C, if we can check, because wait.
yeah,
Yes, I mean, I'm only selecting this because we covered powers of matrix today,
right, yeah,
because of diagonalization. So just so that things stay relatable as opposed to being all over the place.
yeah, yeah.
Uh,
So if, what is the, choose the set
yeah,
of
yeah.
option C alone. So
Maybe we should have done this one first, but okay. Anyway,
right,
let's. But okay.
A is 2022, then a power 10 is
Okay.
1010.
Here they have done the generalization, I think, and they want us to assess whether it is
Exact. Yeah,
or
yeah,
not.
yeah. You're right. So, mm,
But which part of the condition do we as wait? I mean, because I'll have to, if A equal then if okay. So it's a simple if then only, and no
right, right. Yeah,
no compound condition. Okay.
Yeah, so I guess it's the same thing, just that we'll have to multiply. So 2022, right? So if we do a is what 2022, a square is, I think we just have to just try it out, right? So we just need to verify if this is correct, right? A power 10
Um,
is okay. So a square, we can just try it out and see if so a square is 2 into 2 4, and so that's just 4, right? So 2 0, then 2 into 0 plus 0 into 2, and then 2 into 2 plus 2 into 2, so that's 4 plus 4 8, and 2 into 0 plus 2 into 2, right? So 4. So that is, if we just take the 2 out, it's 2 0, 2 0. Sorry, if we take the 4 out,
4 out, yes.
it's 1 0 2 1. Okay, what do they want us to do? Okay, so this is 2 power 10.
2 to the, okay.
So it's like 2 power k 1 0 k 1, right? So 2 power, so it's 2 square into 1021, right? So that is what they want us to verify.
Uh, can we also use the diagonalization
Here,
technique,
ah,
PPD
okay.
to match that thing?
Right, right. Yeah, I believe we can. So let's just quickly see if, so this part we haven't discussed, right? What is, first of all, we have to know if this is diagonalizable. So
Yes,
it's
yes.
like,
First we have to check that.
yeah. So if you look at the characteristic polynomial here, right? So it's lambda square minus 4 lambda plus 4, right? Equal to 0. So 2 square, yeah, that's the determinant, right? So it's 2 into 2. So this implies lambda,
Okay. For the matrix A, right?
yeah, for the matrix A, right? So for the matrix A, so lambda will therefore be 1 and 1, sorry, 2 and 2. So both the eigenvalues are 2. The question is, the only question is, it will be diagonalizable only if, so this is another thing that we didn't discuss. Uh,
Okay. Then
so
maybe let's discuss now.
yeah, so matrix is diagonalizable if and only if, right? The implication is both ways.
Okay.
It has a set of n linearly independent
Independent. Okay.
eigenvectors, right? So a matrix, so if you can, you have to be very rigorous. A square matrix of order n is diagonalizable if and only if it has a set of n linearly independent eigenvectors. So for the eigenvalue 2, we should be, since that is the only eigenvalue available, we should be
Yes.
able to find two linearly independent eigenvectors here for it to be diagonalizable. So we can quickly check if that's the case. So a minus 2i, and that should be 0, right? So this is the eigenvector. So this is like 2022, right? So 2022, so 0 0. Is that correct? 2 minus a minus lambda I will give us 0 0 2 0, correct?
Uh, yeah, I mean, I have to check. You you do have a certain speed.
Oh,
Okay.
sorry. Yeah. So a minus 2, a minus lambda I into v is 0, right? So this is what we are doing. So this is
Okay.
the, so this is what 2 0 0. Okay. What is a? A is 2022, right? So 2022 minus lambda. So minus 2 minus 2,
Yeah. These two will.
right? So, and this is v1 v2 is 0 0, right? So this will give us 0 0 2
Yeah.
0.
uh,
Okay. Now, unfortunately, I think,
Yeah. Unfortunately, yeah. There's
yeah,
this one.
right, we only have one linearly independent eigenvector, so we can't diagonalize this. So we have to rely on pure matrix algebra alone, or the conventional methods to,
Yeah. The way we were going. Okay.
right, right.
Okay.
But it's a useful thing to do. So can we diagonalize? So the answer is no, because the matrix A doesn't have two linearly independent eigenvectors, right? So independent. Okay, so then we fall back to that. old method. So I think we can use that same induction, right? So a power k is, I believe, 2 power k into 10 k1. So and then we 10 k1, and then we try to establish, is this true? So we can do that, right? So a power k plus 1, we can multiply by a. So using the inductive hypothesis, we can plug this in, and this is 2022, right? A is 2022, A is 2022, and we just have to verify if this is true. So 2 power k, and this is what, 2 0 and 2k plus 2 and 2, right? So this is what it becomes. So this k 1 1 2 can come out. That will make this 1 0 k plus 1 2, right? So, or rather 1, and that we have shown. So this is now nothing but a power k plus 1 should be ideally 2 power k plus 1 1 0 k plus 1 1, right?
Yes.
So this is just, we can use induction again. So, and then yeah, but that is a good idea to check for diagonalizability, but we were not, because yes, that in this case it was not useful.
Yes. Okay. Okay. Cool. Then I think we can maybe now
Sure, yeah.
wind up.
Yeah, sure.
Yeah, it's almost 9. So okay. I hope there are more problems like this one in the whether in the assignments or the activity questions, so that I can also try
Yeah,
them
so
out.
there are, but you can also look for questions from textbooks, right? So there are,
Yes, there are some suggested textbook. Yeah.
yeah, so they will have a lot more interesting questions. So
Yes, of course, of course.
okay,
Cool. Uh, Thank you, sir. Then.
yeah, sure, yeah.
And